Now we will continue on with Chapter 8, and we'll look at soils and mass movements in this video. So first of all, weathering is a key process in the formation of soil, and that's why we discuss soil in this chapter. It kind of seems like, oh, this is kind of a weird place for it to go, but soil is only formed because of the weathering processes. And of course, it is one of our most indispensable resources, and we kind of take it for granted. Back in Chapter 1, we talked about Earth as a system, and how we had, four parts that interacted. We had, the geosphere, the atmosphere, the hydrosphere, and the biosphere. And soil is an interface, or a place where different parts of the system interact. And in the case of soil, it's all of the above. The geosphere, the atmosphere, the hydrosphere, and the biosphere, they all meet in soil. So soil develops in response to environmental actions among those different parts of the Earth system. So the biosphere, because we have living organisms there in soil, the air, okay, our atmosphere, the hydrosphere, water and rain, as well as the geosphere, where we get, rock particles that are so weathered that they become soil. Soil will gradually, over time, evolve to a state of equilibrium or balance within its environment. Soil is sensitive to all of the different parts of its surrounding. So when we look at soil, we have to kind of look at the surface of Earth as a whole. So the land surface of Earth is covered by regolith. Regos means blanket, lith of course means rock or stone. So this regolith is the rock and mineral fragments that are formed as a result of weathering. So we have all of this debris plus some organic matter, water, and air. And of course, the organic matter, water, and air are what actually support, the growth of plants. So these four components are always present in soil. So we have mineral matter, air, water, and organic matter. About 1/2, as you see there, is a mixture of the mineral matter that's, been weathered, the disintegrated and decomposed rock, and humus, which is the organic matter. Those are the remains of living organisms. And then the other half is made up of air and water. So if we look at soil texture and structure here, if we look at soil, the particles are not uniform. The particles are going to be all different sizes. So soil texture refers to the proportion of those different particle sizes. So we have sand that is large particles. We have silt that's kind of in the middle, and then clay will have those small size particles. Texture is important because it influences the soil's ability to retain water and air. And of course, we know that both of those are necessary for the growth of plants. So the U.S. Department of Agriculture has developed this soil texture diagram that shows the different types of soils that we can have based on the percent of the particle sizes that they have. So sand, silt, and clay. So if we look over here at point A, we have this area that is sandy clay. Sandy clay here that you see is going to be about 40% clay, about 50 60% sand, and then it's going to be composed of, about, let's see if we follow our silt line down, about 10% silt. So you can see how these lines kind of intersect here. So the blue line represents sand, the red line represents clay, and the green line represents silt. So at this junction here at figure A would fall into sandy clay. The loam soils that are down here that are composed of less clay and more silt, they are and especially this loam and clay loam here in the middle, they are where we have kind of a mixture, and pretty much an equal mixture of the three types of particles. And these loam soils are the best to grow plant life in. They hold moisture and nutrients better than the clay soils or sand or silt on their own. So this sandy loam, silty loam, sandy clay loam, silty clay loam, these are good agricultural soils. Now, if we look at soil structure, soil particles tend to clump together to form these beds that give it a particular structure. We have four basic soil structures you see there: platy, prismatic, blocky, and spheroidal. And this is important because it influences how easily the soil can be cultivated. So is it, suitable for agriculture, as well as how susceptible it is to erosion. It also affects its porosity and its permeability. So can water penetrate, and how is water transmitted within the soil? So when we look at soil formation, what controls soil formation? So there are 5 basic factors that control formation. So the first thing we look at is the parent material. What kind of rock is forming the soil, and where did it come from? And so that's called our parent material. Parent material can be the underlying bedrock, which we call residual soils, or it can be a layer of unconsolidated deposits, and we call those transported soils. Transported soils form in place on parent materials that have been carried from elsewhere and deposited, either by gravity or by water or glacial movement or wind. So residual soil, the parent, is the bedrock, and transported soil, the parent material has been carried from somewhere else, and then it starts to break apart, and so that would be our transported soil. Parent material can influence soil formation in 2 ways. First of all, what type of material it is can influence the rate of weathering, and thus the rate of soil formation. So as we saw in the last video, different types of rock, different types of minerals weather at different rates. So depending on our parent material, we can have different rates of soil formation. The other way parent material influences soils is the chemical makeup of the mineral matter will influence the fertility of the soil. So, and that determines what the soil can be used for, whether it can be used for agriculture or not. The second factor that we have to consider is climate. Climate is the most influential factor in soil formation. Temperature and precipitation exert the strongest impact. As we saw again in the first part of chapter 8, that temperature and precipitation were very important to the weathering process. So and those determine whether chemical or mechanical weathering predominate and influence the rate of weathering. The amount of precipitation also influences the degree to which various materials are removed from the soil as water starts to percolate through the soil, and that also affects soil fertility. The third factor is time. Of course, time is important in all geologic processes. We know that these types of processes happen very slowly over many hundreds or thousands or millions of years. So it takes time to develop these different soils. And so we can have immature soils and mature soils, as we're going to see a little bit later on. And so the longer a soil has been forming, the less it resembles its parent material. Then, of course, we have plants and animals. We know that, the soil contains part of the biosphere. And so the types of organisms that are there and how many organisms will influence the properties of the soil. Plants and animals furnish organic matter to the soil. Of course, plants being the #1 contributor. Soil fertility depends on how much organic matter is present. We also have microorganisms like bacteria and fungi that play a role in plant and animal decay, and this contributes to that humus that I referenced a while ago, that deep, rich organic matter that's so important for soils. And then we have burrowing animals and earthworms, and as they burrow through the soil, they're mixing the minerals and the organic portions of the soil together. And then the last factor that we have that's going to influence soil formation is the topography of the landscape. Variations in topography can lead to differentiation in soil types, even in the same geographical area. And the differences that we see tend to be based upon the angle and orientation of the slopes. So on steep slopes, we don't tend to see mature soil formation. Water runs off so quickly that it doesn't have time to soak in. So the moisture content is not going to allow for vigorous plant growth. And this is going to lead to increased weathering and increased erosion. In the bottomlands, where we have, flat land, these types of soils often stay waterlogged. So they have a lot of organic matter that's a part of them because they're decaying. They can't properly grow because there's too much water, so they decay. The optimum terrain is flat to undulating upland surface, because these types of surfaces are going to have good drainage because they're flat. They're going to have less erosion, and water is going to have time to soak into the ground. And then the other factor with topography is the orientation. This is the direction that the slope is facing. Is it facing north, south, east, or west? In the northern hemisphere, where we are, the south-facing slope receives more sunlight than north-facing slopes, and that causes differences in soil temperature as well as moisture, because it affects precipitation. So we have, all 5 of these factors: topography, climate, time, parent material, and then living organisms, but they all work together to form soil. So when we look at the soil profile, okay, so this is the soil forming processes. They start at the surface, they work their way down. And as that happens, we get these soil horizons or zones or layers of soil. And in our typical temperate region where we live, we will see these different horizons. And this constitutes what we call a soil profile. So this right here would be a soil profile, where we're basically taking a chunk of soil out, and we're looking at the different horizons that we can see within them, and each one of them is important. So now we're going to watch a video about the different soil horizons and why they're all important.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the sequence for the different horizons that are found in a typical soil profile, and you should explain why those different horizons are where we find them. So soil is really important. It's the substrate in which we grow the food that we eat, or we grow crops that we feed to livestock that we then eat. Soil is essential for feeding the human population, so it's important to know something about it. Soil is about half solid material and half empty space. The solid material basically is divided up between a majority of mineral matter, so these are rock fragments and mineral grains, chemical residues, things like that, and then a smaller proportion that is organic material or humus. The rest of the soil is empty space, and that empty space can be occupied by air or water depending on the climatic conditions at the time. This is a look at a typical soil profile. Soil profiles vary from place to place, but typically you'll see these general horizons. We start off at the top with the O horizon. The O horizon is basically dominated by organic materials, plant fragments and things like that. Below the O horizon is the A horizon, and this is where we find mineral matter that's been mixed in with some humus. Below the A horizon is the E horizon, and the E horizon basically forms when rainwater percolates down through the soil and it leaches out material from the mineral matter in the A horizon and the E horizon. Basically, it's dissolving away material and then carrying it down through the soil profile as it percolates in. Some of that material ends up accumulating at the B horizon. So the B horizon basically is a spot where there's accumulation of clay that's been transported in from above. So some of the clay that you find in the B horizon didn't start off there, it was transported in from, say, the E horizon or the A. Now, the O horizon and the A horizon together are called the topsoil, and they're so rich in organic material so that they appear quite brown, usually a very dark color. The B horizon is often known as the subsoil. And together, all the layers that have been discussed so far, O, A, E, and B, are referred to as the solum, or the true soil. Below the true soil is the C horizon. This is partially altered parent material, so basically rotten bedrock. And then below that is the bedrock itself, unweathered parent material. Here are two examples of soil profiles, one from South Dakota on the left and one from Puerto Rico on the right. So you can see that there are certain horizons that will stand out to the eye. So here, for instance, you can see that O horizon up at the top. You've got the A horizon that's still dark. So together, those two are the topsoil. Here's the E horizon that's been eluviated, so it's had material leached out from it, and then the B horizon below that. The example in Puerto Rico is more gradual, where you see basically a change in color from top to bottom, but definitely you can still see the organic material is at the top. How about this example here? Is this something that you're ever going to be likely to see out in the real world? And if so, how would it form? Hopefully what you said is that this is an unlikely situation to be stable in a soil anywhere in the world. But you could actually get something like this, where you had an earlier well-developed soil profile, and then maybe a flood or something deposited a bunch of mineral matter on top of it, and then new organic material accumulated up top. So you could end up getting a preserved topsoil layer in a soil profile, but it's not going to last very long. You know, once the processes of alluviation and leaching go to work on this, you're going to end up rapidly reorganizing this stuff into something that looks more typical. Thanks very much for your attention. This has been another Smart Figure.
Now, something that we have to really be careful about is soil erosion. And soil erosion can have devastating effects on the environment. It is a significant problem, and it's a growing problem as we humans continue to disturb the environment. So when we look at different processes that erode soil, first of all, we look, of course, at water. And you see this picture here of the impact that a raindrop can have on soil. You see there they can have velocities of close to 35 kilometers per hour. So when a raindrop, hits a surface, especially if it's a dry surface or a loose surface, then these raindrops can splash or when they splash, they make the particles, go up in the air and then land away from the impact. And so then as water starts to flow across the surface, as it accumulates and starts to flow, then it's going to carry these dislodged particles away. And this is called sheet erosion. And after that starts flowing, then current develops, leading to rills and gullies. Flowing water is believed to be responsible for up to 2/3 of all erosion that happens to U.S. soil. And then wind erosion contributes the remainder. When it's dry and there are strong winds, and they can pick up, large quantities of soil. We see this happen, especially in the Midwest, where we've had the Dust Bowl and these dust storms. And what you're seeing there is soil erosion caused by wind. Now, soil erosion is the fate of all soils. Farming, logging, and construction will really disturb soil. They disturb the natural vegetation, which act as a barrier to prevent soil erosion. And so without plants, that just accelerates the rates that erosion occur. Rates vary, of course, from place to place. They depend on what type of soil there is there, the climate, the slope, and of course, vegetation. So what do? How do we control soil erosion? Well, we have to do something, because what we're finding is that the rates of soil erosion are exceeding the rates of topsoil development. So what this leads to is lower productivity in terms of, our agriculture, poorer crop quality. This leads to reduced agricultural income. So then you have, farmers that are leaving the profession. So all of these can have, a devastating effect on our food supply and the economy. So what do? Well, soil conservation is a big deal these days. We have, soil conservation experts that are, working with farmers to try to figure out how to prevent the loss of topsoil. So leaving steep slopes undisturbed if at all possible. But when slopes are formed, terraces can be constructed that help prevent the loss of erosion. We can, on gentle slopes, we can plant areas that allow for drainage, but trying to follow the contours of the land. Grassed waterways. So this would be like in between crops. Instead of leaving it bare soil, plant grass there, which is going to help prevent the topsoil from washing away. And then to protect from wind erosion, you can plant small trees or shrubs that act as barriers to wind. And so all of these are shown on page 251 for you, but here is one example. This is where you have corn that's been planted there, and then also hay or grass. And they're planted in strips that kind of follow the hillside. You can see this kind of gently sloping hillside. And it slows the rate of water runoff as it goes down the hillside. By reducing the rate of water runoff, by having all of these vegetation breaks in here, then that is going to lessen the amount of soil erosion that occurs. Now, to switch gears again and cover our last topic for chapter 8, we're going to look at mass movements. And so mass movements are when we get the downslope of rock, regolith, and soil due to gravity. So gravity is the controlling force, but there's often going to be some type of trigger that is going to cause the loss of the rock and the regolith and the soil. It's typically not going to happen on its own. There's going to be some type of trigger mechanism, and we'll go through those. So slopes, of course, we know can consist of rock and rubble, or there can be soil. It can be covered with vegetation, but slopes are ever changing. They are not static because gravity is going to influence their development. We can have, a rock avalanche that is, huge and makes the news because of its destruction, or we can get very gradual and almost imperceptible movement that's occurring along slopes. So when we think about mass movement, we think about, landslides. And in your book on page 253, you've got this Geographics 8.3 that shows you some of the devastation caused by landslides. But landslides are major geologic hazards, but when we use the word landslide, we use it to refer to a lot of different things, rocks, mud flows, the slope, coming off the side of a mountain. So even though we use that term, it's really not a technical term. It's not a geological term. It really can be used to refer to a lot of different things. So that's why we use the term mass movement. Mass movements are not the same as the weathering and erosional processes that we've talked about here, or what we're going to talk about in chapter 10, because there isn't a transport medium. This is all done by gravity. So when we look at mass movement in terms of landscape development, it is the step that follows weathering. If you remember from part 1 of chapter 8, you watched a video about how the Grand Canyon was formed. And so it started out with weathering. And then we had mass movements that occurred on those open rock faces. So once weathering has kind of weakened and broken the rocks apart, that makes them more susceptible to gravity, because now we're on a slope. Now we don't have this smooth, flat surface. We've got a slope that can be triggered by different events. The combined effects of the mass movement and running water produce our stream valleys, okay, like we saw with, the Colorado River carving, the Grand Canyon. And then in the next chapter, we'll talk about how glaciers, groundwater, waves, and wind also transform the land. Earth's mountain building and volcanic processes produce these slopes through sporadic changes in the elevations of land masses and ocean floor. So as long as we have slopes, we're going to have mass movements. Our most rapid types of mass movements typically occur in areas of geologically young mountains. And so as the mountain ages, doesn't have as steep of slopes. And so we have smaller, less noticeable, less spectacular types of mass movements. Now, when we look at some triggers of mass wasting, you know, whether a slope fails or not depends on the balance between gravity, which is pulling, you know, trying to pull the slope downward, and then the strength of the soil and the rock there to resist that force of gravity. But there are several things that kind of interfere with this or can trigger the downslope movement. There are going to be processes at work that reduce the slope stability, making it over time more susceptible to the pull of gravity. And then finally we get to the point where we're, you know, going from stable to unstable, and then we trigger it. And so we're going to look at the role of water, oversteepened slopes, removal of vegetation, and earthquakes as 4 different triggers that are possible to cause these mass wasting events. So when we look at water, mass movement can be triggered by heavy rains or melting snow, and then they saturate the underlying materials, the surface materials, then the underlying materials. The water is not actually transporting the material. What it does is it makes the material more susceptible to be carried away by gravity. Okay, so the gravity is what sets the material in motion. When the pores in sediment become filled with water, the cohesion is destroyed. Okay, so we have dry sand, damp sand, and wet sand. So in dry sand, they're bound by friction, so they're going to stick together. And if they get a little bit wet, then it increases the cohesion, so they even stick together a little bit better. But if enough water is added, then it gets in between the grains and it starts to separate the grains, and so it's going to tend to spread out in all directions. So as it oozes out, anything overlying it can be set in motion by gravity. When clay is wet, it becomes slick. And so that is another effect. It becomes slick. It doesn't want to stick to the underlying surfaces, and so gravity can set it in motion. The other thing we have to look at with water is water adds weight. So the weight itself can be enough so that the force exerted by the rock and the overlying soil is not enough to overcome the force of gravity. So now we'll see, we'll take a mobile field trip. We're going to go and look at some landslides that have happened out west. And most of these have been triggered by water. And when I say landslide, again, it's hard to get that word out of your vocabulary, but we're looking at some different types of mass wasting events.
Hello, I'm Michael Collier. I'd like to take you on a freewheeling tour of landslides around North America. We'll cover a lot of ground, but most examples will be from mountainous regions. One of geology's enduring truths is that, in the end, gravity always wins. Whenever material gets stacked too high, it eventually falls down. So all else being equal, the steeper a terrain, the more likely it is to have landslides. Landslide is a convenient but not very specific term that encompasses many types of rapid mass wasting. Solid rock, loose sediments, or snow can all suddenly move downhill. Depending on which material is moving and the geometry of its descent, a landslide might be a rockfall, a debris flow, or a volcanic lahar. Each is a specific type of mass wasting. On this field trip, we'll lump them all together as landslides. Even though we'll be looking at a variety of examples, we'll try to understand what properties landslides have in common, what's likely to trigger them, and how they can affect people's lives. Landslides are more likely to occur in Kansas, Florida, California. Landslides are far more likely to occur in mountainous California. The Blackhawk Landslide occurred 17,000 years ago in California's tectonically active San Bernardino Mountains. Here, Paleozoic limestone has been thrust over uncemented sandstones and weathered gneiss. The soft, underlying rocks were eroded, creating a steep and unstable cliff. Perhaps moist conditions of the Quaternary Ice Age saturated the sandstone. Did an earthquake along the nearby San Andreas Fault shake the overlying limestone loose? Who knows? What is clear, though, is that a block broke loose and hurled a blanket of debris 5 miles out onto the Mojave Desert. There's a pretty good chance that the slide magically rode a carpet of compressed air that was trapped when it ski jumped a ridge midway in its descent. We do know that a magnitude 8.3 earthquake struck Alaska's Fairweather Range in 1958. 40 million cubic yards of rock were shaken loose and swan dived 3,000 feet into the waters of Lituya Bay. The rockfall generated a 1,700-foot wave that ripped across an adjacent ridge. Try to imagine it. A wave 1,760 feet high. The wave was only 200 feet tall when it swept over Cenotaph Island, halfway down the bay. 3 boats were tethered nearby. Incredibly, the occupants of 2 boats survived. 50 years later, you can still see trim lines where trees were snapped off for many miles down bay. Landslides can be lethal. During the last century, 6 out of 8 of the most deadly ones happened in the mountainous west. Quake Lake formed overnight when a magnitude 7.5 earthquake shook southwestern Montana in 1959. 28 campers had no chance of outrunning the 100-mile-an-hour slide that instantly blocked the Madison River. Unscathed lichens show that this house-sized dolomite block floated on top of the 80 million tons of rock that slid off Sheep Mountain. Landslides can have a variety of triggers. Earthquakes are an obvious one. Another occurs when a sudden influx of water fills pore spaces between grains and reduces cohesion among rocks on a slope, thus triggering a landslide. A 3-mile-long debris flow in May 2014 was triggered when a winter's worth of snow began to melt on Grand Mesa in western Colorado. Multiple mud flows surged down Salt Creek. This is where one of the first pulses jumped a 200-foot ridge and fanned out toward valleys on either side. Water ponded up again at the head of the slide, adding to the risk of further activity. 3 men died when they were engulfed by subsequent flows. No homes were destroyed, but numerous oil and gas wells are in the vicinity. What hazards are created when a landslide engulfs an oil well? Certain geologic configurations can add to the likelihood of a landslide. Pre-existing fractures like faults and joints can weaken a block of rock and add to its risk of sliding. Rocks are more likely to slide when sedimentary strata have been tilted into an alignment that favors the work of gravity. This was the case in western Wyoming in 1925, when 50 million cubic yards of the Tin Sleep sandstone slid down a tilted ramp of the slippery Amsden Shale. The slide crossed the Gros Ventre River and raced up the other side of the canyon. The river was blocked, and a new lake quickly rose behind 200 feet of debris. Sadly, 6 people drowned 2 years later when the unconsolidated dam unexpectedly gave way, washing out the town of Kelly 6 miles downstream. Volcanoes can pile up a lot of over-steepened ash along their flanks during an eruption, and rain subsequently turns that ash into cement-like soup called a lahar. That's what happened after Washington's Mount St. Helens erupted in 1980. Lahars soon rushed down at 90 miles an hour, destroying dozens of bridges and hundreds of homes. 185 miles of road were erased. In the months following the eruption, 65 million cubic yards of ashy sludge were dumped into the nearby Cowlitz and Columbia rivers. Landslides transport material from high places to lower places. After the first devastating seconds are over, rivers are usually left to mop up the debris. But that's not always the case. When Alaska was violently shaken by its great earthquake in 1964, 3.25 million cubic yards of rock and ice slid onto a glacier near Cordova. In the 50 years following the landslide, its blanket of debris has been carried further downhill, not by a river, but on the back of the Sherman Glacier. During that time, the blanket has insulated ice that would otherwise have melted. Our final stop on this landslide tour is along the Stillaguamish River north of Seattle. The region had received higher than normal precipitation before the Oso slide occurred in 2014. Slides had happened above the tiny community of Oso many times before: 1949, 1951, 67, 88, 2006. The valley was a setup, its bottom filled with unconsolidated glacial till left by retreating glaciers just a few thousand years ago. On March 22nd, 10 million cubic yards of sand and mud suddenly slid away from a 600-foot head wall and rushed across the Stillaguamish. 45 homes in Oso were destroyed. 43 people died. Rescue efforts were difficult because the landslide had liquefied as it fell. The debris just turned into jelly. Mud sucked like quicksand at the rescuers' boots. Can landslides be predicted? With so many recurrences along the Stillaguamish, this question certainly must be addressed at the Oso slide. Had logging weakened the till by removing vegetation or redirecting groundwater? Should homes have been built here in the first place? Could lives have been saved if an early warning device had been monitoring slopes across the river? Risk assessment is challenging and expensive when geologists try to anticipate slides throughout large regions that may have combinations of steep topography, earthquakes, heavy rain, or other factors that can all add up to a landslide. What did you learn? Which landslide was not triggered by an earthquake? Lituya Bay in Alaska, Salt Creek in Colorado, Madison River in Montana. The landslides at Lituya Bay and along the Madison River were triggered by earthquakes. Salt Creek in Colorado was caused by a sudden increase in meltwater.
So you saw there several examples of mass wasting caused by water and then a couple by earthquakes. So we can also have mass wasting events that are caused by oversteepening of slopes. As the slope becomes steeper, the forces that resist that downward pull of gravity get weaker. Human activities often create oversteepened slopes that can become sites of mass movement. Oversteepening has a particularly clear-cut effect on slopes made of loose granular particles, sand-sized or coarser. If you look on page 255 in your book, I don't have a picture of it here in your PowerPoint, but in figure 8.25, you see these oversteepened hill slopes here, and we've got, heavy rainfall, and heavy rainfall down this slope makes it unstable, and you can see that it basically has a mass movement event that is going to destroy this house that is sitting there kind of in the middle of this slope. You see this angle of repose here. This is the angle at which the materials are stable. Larger, more angular particles can have a larger can maintain steeper slopes, so they can have a smaller angle of repose. But if the slope is steepened beyond its angle of repose, then the materials are going to start to slide downward until they adjust that angle. So you've seen that, earthquakes can be triggers, conditions favoring mass movement. Those slopes can be stable for a period of time and, no movement is occurring. And so we need an additional factor, and that can be the earthquake. An earthquake and its aftershocks can dislodge, of course, enormous volumes of rock and unconsolidated material. And then another trigger is the removal of anchoring vegetation. So as we've seen already, plants help to protect against erosion. They contribute to the stability of slopes because their root systems go in and anchor the soil and the regolith together. So that helps, prevent erosion. Plants also shield the surface from erosional effects of water and rain. where we don't have plants, where we don't have vegetation, mass movement is enhanced, especially if we look at the angle of the slopes. When anchoring vegetation is removed, surface materials tend to downslope. So we tend to get these mass wasting events. Now, one thing you may not think about in terms of, removal of vegetation and triggering these mass wasting events are wildfires. When wildfires come in and they wipe out all of the vegetation in an area, and then that's followed by intense rainfall, we can get very fast moving debris flows that can really just wipe out these slopes. And they tend to occur with little warning. People don't know that they're coming. Post-fire debris flows are most common in the 2 years after a fire. So last month in Arizona, there was a flash flood that resulted in the aftermath of a particular fire that happened about a year or two ago. And because that fire had done so much damage and had destroyed so much of the vegetation, the water was able to flow with insane speed through this town of Globe, Arizona. And I found a news program that shows a time-elapsed video of this flash flood moving into town. And so we'll watch that now.
Just how quickly that flooding in Globe happened. So this is video from Bonnie's Pizza right there in Globe. And you saw it, just a little trickle. We sped it up for you because it lasts about 4 minutes. This is on their Facebook page. So
look
watch,
at that.
It's getting higher and higher. There go the barrels. There goes the sign as we keep watching this. And I think it was right in this area where the US 60 shut down. So let's bring in the owner, Joe Stapleton of Bonnie's Pizza. Joe, your surveillance camera really capturing this. First of all, I understand you have a lot of flood damage. I'm sorry about that. Tell us about what happened yesterday.
Well, my son, he works at the hospital. He's a nurse there. And he's the one that warned us, and because he was driving toward the hospital on this emergency exit and entrance to the hospital, which was underwater. But he's the one that called us and told us about this, and we didn't really believe it that much because I've been here for 63 years, and this has never happened.
Wow.
But we were looking over the railroad track.
Right.
We got other films. We were looking at what we call the railroad track, which is a berm behind us with a track on top of it, and the water was coming over that, and it's about, I would say, 8-10 feet on the other side. So, and the water just started coming over that thing, and it was in minutes. We had to, evacuate our building.
That dumpster go by. Sorry, Joe. We're watching your videos.
We're watching this.
Oh, yeah. This film right here, where you can see how fast this water is coming in, and we were all... These are the people back at the hotel. They were wondering about evacuating, so we got everybody out, and everybody was safe. Thank God, everybody. This thing is so fast. It's really amazing how this water can make damage and pretty much scare the crap out of you.
Absolutely.
Sorry to say those words on live TV, but it was very frightening to a lot of people like myself. Especially losing the business. We didn't lose it. We surveyed very minimum damage. Our neighbors, which is the smoke shop, they got more damage than we did. And I see the dumpster going by right now.
Yeah, it really is crazy.
That just missed our gas meter. That's my son running.
Oh my gosh.
Oh wow.
That would have been really bad, right?
It was just, everything just so fast. We didn't have time to get out. It was... Go ahead.
Joe, are you inside the building as while all of this is going on?
Yes, the storm was up in the what we call the canals, and that's where all this water is coming from. It's coming from the burn area behind us. The culverts that go through underneath the highway. They weren't able to handle all this water.
Oh yeah, look at that. You can see that it's all full of debris almost right there in that shot you just had.
Yeah, there's so much stuff coming down. It's just, We got about I would say about 2 foot of water inside the shops, and mud. The mud is terrible. That stuff is hard to clean.
So, we're watching this again, and so we said it was about 4 minutes. So in 4 minutes.
So you saw the amount of water that came in just in 4 minutes. But, you'll notice if you kind of look in the background here, you see these steep slopes. Yep, there's grass on these. These back in the background here, don't really have as much vegetation there. And this is kind of the way it is surrounding this town, and this town kind of sits a little bit down in a valley. And so when you lose all of the vegetation here, water is just going to flow extremely fast. And they had not that much rain, but it triggered these massive flash floods because of the lack of vegetation. And you also saw, when you were looking at some of the water coming through here, you did see a lot of, limbs and other debris that were taking out, you saw the signs and the barrels and the dumpsters and everything floating by. So this just kind of shows that the wildfire is not the only devastating thing that can happen. It can trigger events like this as well. So the last thing we're going to talk about here in Chapter 8 are the different types of mass movement. We can classify mass movements by the type of material involved, the kind of motion, and the velocity of the movement. So in looking at our type of material, if soil and regolith dominate, then we can use, debris or mud or earth. But when a mass of bedrock breaks loose, then we tend to call that, a rock slide or a rock fall. When the mass movement involves the free falling of detached materials, we call that a fall. And this typically occurs on slopes that are too steep for the loose material to remain on the surface. Slides are when the material remains fairly coherent to one another, but then moves along a well-defined surface. We can also have a slump, which is kind of a type of slide, is when the descending material slides along a curved surface. And then the third type is called a flow. Flow occurs when the material is going to move down slope as a viscous, turbulent fluid. And then we look at the rate of movement. Is it fast or slow? In rock avalanches, the rock and other debris can go down the slope at speeds approaching 125 miles an hour. And because of this momentum can continue to flow even for long distances after the slope has ended. But most mass movements don't move like that. Most mass movement is actually really slow. And so we'll look at a few of those as well. So the rapid forms of mass movement that we can see are slumps, rock slides, debris flows, and earth flows. And these are more common where slopes are steep. And the speed here varies from barely perceptible to very rapid. So we have slump, which is rapid movement along a curved surface. We typically see this on over-steepened slopes. So again, they've gone over their angle of repose, and the soil here and debris cannot stay on that angle. Rock slide is a rapid movement where blocks of bedrock break loose and then just slide all the way down a slope. So you'll have this surface of rupture and everything will just slide off. A debris flow, or sometimes called a mud flow, this is debris with water. Sometimes we'll see it confined in these channels, as you see here. And this can also be like the lahars that we looked at that are associated with volcanoes. And then we can have earth flows, which are another type of rapid movement. We see these on slopes typically that aren't as high. Water saturates the soil, and it then you get this little bit of a kind of a slump here, and then it just slides downward. So we also have a couple more that aren't demonstrated here. We're going to watch a video on these, but then we also have creep and soliflucation, which are slow forms of mass movement. Sudden movements actually transport less material than the slow action of creep. Creep can take place on both steep and gentle slopes, so it's going to be more widespread than the rapid forms of mass wasting. Creep involves the gradual downhill movement of soil and regolith. And one of the factors here is the alternating expansion and contraction of the surface material on those freeze-thaw cycles that we looked at that could contribute to, mechanical weathering. They also contribute to creep. Soliflucation, which means soil flow, occurs when the soil becomes saturated with water, and it can flow down slope at a rate of a few millimeters to a few centimeters per day or per year, depending on the slope. And we also see this in regions that have the permafrost. The upper region becomes saturated with water, and it's going to start to flow over that frozen surface below. That frozen surface gives it, a smooth surface to slide along. So now we're going to watch one last video here showing us these different types of mass wasting.
Mass wasting. Mass wasting, or mass movement, entails the relatively short distance downslope movement of weathered rock under the direct influence of gravity. The different kinds of mass wasting are distinguished by the dominant style of movement involved. In the mass wasting process of fall or rockfall, rock fragments loosened by weathering simply fall or roll down the foot of a steep slope. The pieces of angular, unsorted rock that fall and accumulate in this fashion are called talus. Over time, talus may build up into steep talus cones or talus slopes. In the mass wasting process of slide or landslide, a section of hillside fails and large blocks of weathered rock slide downslope. Some landslides are triggered by heavy rain, which adds weight to the weathered rock and may reduce the coherence of soil particles. However, in many cases, a slide consists of dry material. A special variety of slide is known as a slump. When slumping takes place, material moves along a curved sliding plane. For this reason, slump is sometimes referred to as a rotational slide. Both landslides and slumps leave noticeable scars on the hillside where the movement began. Creep is the slowest kind of mass wasting. Creep entails the very gradual downslope movement of the surface layer of soil or regolith. Many factors can cause soil creep. The freeze-thaw cycle, the repeated saturation of hillside soil with water, as well as other disturbances of the soil may all contribute to creep. Often the most noticeable effects of creep are human-built features, such as fences and telephone poles that begin to tilt downhill after a number of years. In the mass wasting process of flow, very wet, weathered rock material flows downslope. The type of flow you see here is known as earth flow. Earth flow develops when a section of a water-saturated slope fails and begins to flow downhill. Another kind of flow, known as mud flow, can develop in mountain drainage basins, especially in arid regions. During a heavy rain, fine debris is picked up from the hillsides by runoff and is concentrated on the valley floor, where it flows rapidly down valley with a consistency of wet concrete. When mud flows contain large boulders, they are often given the name debris flows.
So that brings us to the end of chapter 8 and prepares us to move into chapter 10, where we're going to get to really study erosion a little bit more closely as we take a look at glaciers and wind.